Hi, I'm Rob, and I'd like to welcome you to this video where we'll train a model to make predictions against the PIMA diabetes dataset, evaluate performance, then deploy the model to a web app using FastAPI and Flask into containers on a Docker network. Before we get started, I want to mention that the focus of this video is on deploying a trained model in containers on a Docker network. The data cleansing and model training, evaluation, and exporting that we'll be doing in this video is going to move rather quickly. However, these topics are covered in detail in the prior videos in this playlist. So if you'd like more detail on these concepts as we progress through this video, I recommend pausing and checking out the prior video on that specific topic. Also, if you don't have exposure to working with Docker or need a refresher, I'll post a link to the Docker playlist I have, which should give you enough of a foundation to follow along here. Okay, with all that out of the way, let's get started. In the Jupyter Notebook for the demo, be sure to install the required libraries if they're not yet on your machine. I already have them, so I'll jump down to the next cell and do the imports. Next, I'll instantiate instances of the logistic regression and random forest classifier models, and then install the Kaggle Hub library, which will allow us to get the PIMA Indians diabetes dataset from Kaggle. Alternatively, you could download the file from here and then import it as a CSV. So I'll go ahead and execute the code in this cell. And we see the dataset's been imported as a pandas data frame. There are 768 entries with 9 columns. And all the columns are numeric. And here's a preview of the head of the dataset and some summary statistics. Now let's display a correlation matrix of the features and a heat map. Again, if the concepts we just ran through quickly are new to you, along with the data cleansing that we'll do next, I do recommend going and watching the prior videos on those topics and then coming back and picking up here. So in cleansing the data, the first thing I'll do is check to see if the data frame has any missing values. If it does, we'll just print a count, else no missing values. And then I've defined a function which will check for all columns that have zeros in the cells. And I'll use that function, passing the data frame, to get the list of columns with zeros, and then call replace on those columns within the data frame, replacing 0 with NaN. Then I'll get a count of the columns with zeros and display a bar plot so we could visualize them. Then finally, I'll replace the columns with NaN with imputed values of the median of the column. So let's go ahead and run the code in a cell and take a look at the output. First, we see there are no missing values in the data set. The columns that have 0 for values, excluding pregnancies and outcome, are glucose, blood pressure, skin thickness, insulin, and BMI. And we can see those counts here. We're going to exclude pregnancies because some of the women in the data set may not have had pregnancies. And the outcome column will be the target that we want to perform predictions on. And here's our plot representing the values above. After filling the columns that have NaN with the median of each column, we see that there are no longer any columns that have 0 values, with the exception of pregnancies and outcome. In this next cell, we'll prepare the features and target variables, and we'll start by dropping outcome from the data frame and then assigning outcome to the variable y. Then we'll call train test split to create the training and test datasets. So let's run the code in this cell, and we see the shape of our datasets. Now let's move down and train and evaluate the model performance. Here I've created a function, check for overfitting, which takes the model, the accuracy, and the training datasets. And it will compare the training and test accuracy to see if the training accuracy is significantly higher than the test accuracy, and if it is, it may indicate that the model's overfitting. So we'll start by getting the model score, and we'll do that by calling the score method on the model, passing it the training datasets, and subtracting the accuracy. Then we'll check the result and print the appropriate message. So let's execute the code in this cell to define the function and move on to the logistic regression model. So we've already defined the logistic regression model above, and we're going to call the fit method passing the training datasets, which we got by calling train test split. Then we'll call predict on the model, passing a test dataset, and then get the accuracy score, which will ultimately pass the check for overfitting. So let's go ahead and run the code in this cell. And here we see our training score and the accuracy and the classification report. So now let's call a check for overfitting on a logistic regression model. And we see we have no significant overfitting, indicating that the training and test accuracies are reasonably close. So this looks like a fairly good model to use for our dataset. Next, we'll train and evaluate the performance of a random forest classifier on the data. So let's go ahead and run the code in a cell to train the random forest classifier, which was previously instantiated above. We'll call the predict method on it, get the accuracy score, print the results, and then check for overfitting. So let's run this cell. And looking at the results, we see the random forest classifier has a training score of 100% and an accuracy of 75%. Whereas the logistic regression has a training score of 76% and an accuracy of 77%. So while the random forest achieved perfect accuracy on the training data, its test accuracy is lower than its training score, indicating overfitting, which we'll scroll down and verify. And we see that overfitting is detected in the model, while the logistic regression model shows consistent performance between training and test datasets, suggesting better generalization to new data. So it looks like for this dataset, the logistic regression model appears to be a better choice. Next, we're going to reset and clean the data to make predictions using XGBoost. Now, XGBoost is a powerful, high-performance machine learning algorithm that uses gradient-boosted decision trees to solve both classification and regression problems. You would use it for a diabetes dataset like this because of its ability to handle complex real-world data, provide high predictive accuracy, and it offers features that prevent overfitting. Now, before we load the data, I've declared a function called makePredictions, which will take the model, a scalar, and new sample data to make predictions on the data that was passed in, and then print the result predicting if the patient is diabetic or not diabetic. So let's run the code in this cell to load the function. Then in this cell, I'm going to read the CSV back in, find the columns with zeros, replace them with NaN, and then replace the columns with NaN with the mean of the column, prepare the features and target variables, and then get our training and testing datasets. Here I'm going to instantiate an instance of standard scalar, and then we'll describe the pandas data frame. So let's execute the code in the cell. We see that columns that have 0 values, excluding pregnancies and outcome, are what we saw before for glucose, blood pressure, skin thickness, insulin, and BMI. And here are summary statistics again on the data. Here I'm going to import the XGBoost classifier from XGBoost, so make sure you go ahead and install it before running the code in the cell. I'll instantiate an instance of the XGBoost classifier, then we'll train the model, call the predict method, and get the accuracy score. Then we'll check for overfitting, print the confusion matrix, the classification report, and the accuracy. So let's go ahead and run this code. And for XGBoost, we see a training accuracy of 100%, test accuracy of 79%, and overfitting is detected. And here's the confusion matrix of the prediction results. Now, what I want to do is call the makePrediction function, passing the XGBoost model, the instance of the scalar, and a NumPy array containing patient data for a diabetic patient. Then I'll call the function passing patient data for a non-diabetic patient. So let's run the code in this cell and see the results. And the model returned diabetic for the first patient and not diabetic for the second. Finally, in this demo, what I want to do is create a new logistic regression model, train it with the scaled training data, and then I'll import the joblib library, which will allow me to save that trained model. But before we execute the code in the cell, let's jump over to the Jupyter home screen. And although there's a hefty list of files here, we don't see the exported model. So back in the cell, we'll execute the code. Here we see the joblib file, and if we jump back to the home screen, we see the files listed here. Now if we go back to the notebook, I'll call the load method on the joblib library passing it the name of the joblib file for the exported model, storing it in a variable, and then passing it to the make prediction function with patient data for a diabetic patient, and then patient data for a non-diabetic patient. So let's go ahead and execute the code in this cell, and the results return diabetic and not diabetic as expected. So that was a quick run through of training a model, evaluating performance, making predictions, and exporting the model. Again, if you want to take a deeper dive into any of those concepts, feel free to check out the prior videos in the playlist. Now, let's move on to deploying the trained model and send it patient data for diabetic predictions. Now, to get started, I've cleaned up the project folder so we can focus on creating specific files as we need them and progress through the deployment. Also, I want to point out that the README in this project has the steps for deploying the FastAPI and Flask app, both as individual apps as well as in containers. So feel free to reference that for the commands to execute while you're following along. So let's get started with the FastAPI app, which will interact with our trained and exported model. At a high level, FastAPI is a modern, high-performance web framework for building APIs with Python. Feel free to take a look at the documentation if you'd like to get into specifics of the framework. But for this demo, I'll just focus on the implementation of the API. So to get started, I'll create a new file named api.py. Now, we'll need to use a few libraries, so I'll go ahead and add the imports, and then create a requirements.txt file and paste in the requirements. Now, if I open a new terminal and do a pip install -r pointing to the requirements.txt file, it'll install the dependencies. I already have these installed, so I'm going to skip this step and jump back into the code. So the first thing I'll do is create an instance of FastAPI and assign it to the variable app. Then I'll add a line of code to use joblib to load our model into the app. Then I'll define a class called patient data to define the input model. I'm going to jump back up to the top for a second and add a patient data dictionary with data for diabetic and non-diabetic patients, and scroll back down. I'll add a route for the API health check, a route to get patient data, which takes an integer indicating whether we want the diabetic data or the non-diabetic data, as well as a route for predictions. The make prediction function takes data which adheres to the patient data class. It'll put the data into a NumPy array and then pass that data to the predict method on the model, returning the prediction, which ultimately will return the result to the calling application. So let's go ahead and save this and jump into the terminal, and I'll launch the app, jump over to the browser, and if I go to localhost port 8081/health, we see the health check is returned. If I go to localhost 8081/patient data, passing the diabetic parameter with a value of 1, I get the data for the diabetic patient, and passing a diabetic parameter value of 0 returns the data for the non-diabetic patient. And because this is a FastAPI app, if I go to localhost 8081/docs, I'll get a user interface in which I can interact with the API. So for example, if I expand the get for the health check, click try it out, and execute, we'll see my response status that the API is healthy. If I scroll down to get patient data, and try it out, and leave the diabetic parameter set to 1 and execute, I get the data for the diabetic patient. And let me copy this to the clipboard and scroll down, expand the predict, try it out. I'll paste that data in and execute. And we see our prediction is diabetic. And if we scroll back up and change the diabetic parameter to 0 and execute, we get the data for the non-diabetic patient, which we'll copy to the clipboard, paste in, execute, and we get the non-diabetic response from our model. Okay, with the FastAPI in place, let's switch our focus to building out the Flask app, which will provide the UI which will interact with the API. At a high level, Flask is a lightweight web application framework, and as mentioned, we'll use it to build our user interface. Feel free to take a look at the documentation if you'd like to get into specifics of the framework. So I'll close the API file and create a new app.py, and then drop the code in, which we'll walk through. So as usual at the top, we have our imports, which means we're going to need a requirements.txt file. So I'm going to rename the existing requirements text to API requirements for the FastAPI and create a new app requirements file, which will have the dependencies for Flask and requests. And you can run a pip install -r pointing to the app requirements.txt file to pull the dependencies down. I already have them installed, so I'll skip this step. So after the imports, we'll create a Flask app. I have a variable for the API base URL, which points to localhost 8081, which is the FastAPI server. I have one route, which is the root route, that will respond to gets and posts. And in the index function, I'll check to see if the request is a post. If it is, and if the action is get patient data, then I'll get the diabetic type, which will be the 1 or the 0, and make a request to the patient data endpoint of the API server. If the request is a post and the action is check health, I'll make a request to the API's health endpoint. Else if the action is predict, I'll grab the prediction data from the form and make a request to the predict endpoint. And finally, I'll return the index.html file, which I'll create in a template folder. Now I'm not going to go through the entire contents of the HTML, but I will point out that because this is a Flask app, we'll be dynamically injecting content into the page itself. Then back in the app.py file, I'll run the server on port 5001. So let's go ahead and jump to the terminal and run the app. Now go back to the browser and go to localhost 5001, and we see our Flask app. So let's scroll down here and click the check API health button. And we see the status of the API is healthy. We'll get patient data for a diabetic patient. Then click the populate prediction form with this data. And the reason that this is included is so I don't have to manually populate the form for the demo. And then I'll get the prediction. And as we see, the prediction is for a diabetic patient. And we'll scroll up, get the non-diabetic patient data, populate the form again, and get the prediction, which is non-diabetic. And here we see the full response from the API, which is the model's prediction. Okay, so we tested that we're able to serve both the FastAPI app, which interacts with our trained model, and the Flask app, which provides a UI to hit API endpoints as individual apps. So let's move on to deploying these apps in Docker containers. And as a reminder, if you're new to Docker or need a refresher, feel free to check out the videos in my Docker playlist before moving forward, as it'll help following along much easier. And with that said, and Docker up and running on your machine, let's build a Docker file for the API. Okay, first of all, I've terminated both the Flask app and the FastAPI app in the terminal and created an API Docker file, which I've pre-populated. Here, I'll be using the Python 3.9 Slim base image. I'll create an app workdir, copy the API requirements text file, and then run a pip install, as well as copy the API.py file and the joblib file. I'll be exposing the API on port 8081, and then I have the command to launch it. So if I jump over to Docker real quick, we see I have no containers, which I can confirm with a docker ps-a, and the only images I have are for Kubernetes and Docker Desktop. there are no images related to the Pima diabetes predictor, which I can confirm by running a Docker images, or more specifically, a Docker images grepping for Pima. So to make things easier to see, I'm going to jump back into VS Code, and in one terminal, in the folder with the API file, I'll run a Docker build, passing it the file flag to the API Docker file and giving the image a name of Pima Diabetes Predictor API. So let's go ahead and run this. And jump back into Docker, and we see our Pima Diabetes Predictor API image. So let's go ahead and launch one from the image. And that command will be docker run, exposing the port 8081. I'll give it a name of Pima Diabetes Predictor API and use the latest image. Now if we jump back into the browser and hit localhost 8081/health, we see our API is healthy message. And if we go to /docs, we see the UI we could use to test the FastAPI. So let's do that quickly. I'll try it out with the health check. And our app is healthy. We'll get the patient data for the diabetic patient. Copy the response. And test the prediction. And we see we get the diabetic response from the model. All right, let's jump back into VS Code and create a Docker file for the Flask app. So here I have my app Docker file. It's using the Python 3.12 Slim base image. I'll create an app workdir, copy the necessary files, and run a pip install, passing it the app requirements text file. We'll expose the app on 5001 and then launch the app. In the app.py, I've made a couple changes. I've changed the API base URL from localhost to the Pima Diabetes Predictor API on 8081 to target the app in the container, and changed the app run to specify a host of 0.0.0.0 on port 5001. This is because when running Flask apps inside Docker containers, by default it only binds to localhost, which means it's only accessible from within the container itself. By setting host to 0.0.0.0, the Flask app binds to all network interfaces, making it accessible from outside the container, so we can hit it in the browser. Now, jumping over to Docker, we see we only have the API container and the API image. So back in VS Code, we'll run a docker build command, passing it the app Docker file and giving the image a tag of Pima Diabetes Predictor app. And back in Docker, we see the image, yet no container. So let's jump back into VS Code and do a docker run, exposing port 5001 using the latest version of the Pima Diabetes Predictor app image. Now if we jump back in the browser and hit localhost 5001 and scroll down and try a health check, we see the health check fails because we can't reach the API running on port 8081 in its container from the Flask app running in its container. So let's jump back into VS Code and build a Docker network to deploy the containers into so they can communicate with one another. I'll start by terminating the running process and stopping and removing the container. Now we see the container and images are gone. So close up these files because we don't need them and create a new file named Docker Compose YAML. And inside we'll specify a network of Diabetes App Network, which is a bridge network. And I have two services, one for the API and one for the app. Inside the API, under the build, we see we're passing the Docker file of API Docker file. Its image is the Pima Diabetes Predictor API, and we're specifying container name of Pima Diabetes Predictor API. We're exposing port 8001, and this will run on the Diabetes App Network. For the app, we're specifying the Docker file of app Docker file. This will use the Pima Diabetes Predictor app. We're exposing this on port 5001. It depends on the Pima Diabetes Predictor API, and it'll run on the same network. So let's jump into a terminal and run a Docker Compose up to deploy the resources. Now back in Docker, we see the images and the containers. So let's jump into a browser hit localhost 5001, try the health check, and now we see the API is healthy. So let's get the diabetic patient data, populate the form, and get a prediction, and we see the diabetic result. And we'll get the data for the non-diabetic patient, make this prediction, and we see the non-diabetic result. All right, so back in VS Code, we'll do one more thing. We'll stop the running process and do a Docker compose down to clean up our resources. So the containers are gone, but the images are still there. So we'll run Docker remove image commands to clean those up as well. So that concludes this video on an end-to-end model training, exporting, and deploying with an API and web app on a Docker network. If you found it useful, feel free to give it a like. And if you'd like to be notified when I add more content to the channel, please consider subscribing. Thanks for watching.